In this part of the training module for oceanographic moorings, we're going to look at assignment 3. This consists of looking at a surface mooring for a profiler based around the Del Mar Oceanographic Wirewalker. So in this particular problem and description and constraints, the nature of the problem is working with a Wirewalker profiler in 50 meters of water depth. Now, in the sample oceanographic mooring files, there's actually one already set up for 200 meter water depth. So it's possible to adapt this mooring for this other water depth. It says in the description that a scope of 1.7 seems to have worked well at that range of water depth. And the goal is to profile about 75% of the water column if possible. Watch for any collision with the downweight in the seabed, especially any sustained contact, because that's going to interfere with the mechanism of the profiler, and check what's going to happen with the dynamic mooring tensions in different sea states. So there's some mid-ocean parameters here with current profile and different wave states, and some description about how to go through the process. So that's what we're going to do. If we check over here, in the sample mooring files, we'll see Del Mar Wirewalker 200 meters, so we can actually copy this file into our little assignment folder. Here, let's rename it to 50 meters. There we are. So in terms of trying to establish what's the worst case sea state, technically when you look at the wave steepness, the 3 meter significant wave height 6-second peak period is steeper, the steeper of the two, but the thing is this 8 meters is starting to be a sizable portion of the water column of that water depth of 50 meters, so it's not really totally obvious what'll be the worst case scenario. And so we should check both cases. But first let's get to adjusting the mooring. So very generally, you can see just looking at the 200 meter mooring design, most of the mooring length is taken up by 2 sets of components, this wire rope that's 150 meters long, and then there's also these 2 fiber rope sections, one of which has some floats on it to help just get that S-shaped mooring profile in the water column. So we're going to have to adjust those 2 components, and that'll largely cover most of the mooring modification. So we've got just a little under 1.7 scope here. Let's change the water depth accordingly. So we'll go to 50 meters water depth, and then also let's adjust this other point here, 50 meters, and the current 0 at the seabed. Okay, now first changing the wire rope length. They want to, the nature of the problem wants to try profiling 75% of the water column, so that's 75% of 50 meters, that's 37.5 meters, so we can adjust the wire rope size directly that way. And now, just as a really rough check, with these worst case wave heights of 8 meters, I mean, you can have individual waves bigger than that, but let's just check and see. We want to keep that downweight clear from the seabed. So the downweight would be at the bottom of the wire. We're looking at 50 minus 37.5, that's 12.5 meters clearance from the seabed. Okay, so there's a bit of buffer there, and it's bigger than the 8 meter waves, that's good. Very roughly aiming for a scope of 1.7, that means the total mooring length is going to be about 85 meters. So if we subtract out from that the wire rope length, we've got about 47.5 for the remainder of the mooring. But remember, we need a little bit for the acoustic release and the rest of the mooring, so we could sort of just round down to 40 meters for fiber rope. Now the fiber rope is broken up into 2 sections with floats on one of them, so just to make life easy, we could change this to 20 and change this to 20, and it mentions that we should have the floats somewhere in the middle of the section here, and why don't we put it at 10 meters and then about a half meter spacing. I mean, the floats could be maybe a little bit tighter, maybe a little bit looser than that, but either way, the idea is just to get a design set up here, and then we're going to check and see what the dynamic loads are like in these, pretty strong wave conditions, and verify the strength and so on for the components. All right. So we've made those adjustments, and let's just double check the scope. Okay, it's a scope of 2 now. I mean, that just means there's more, a little bit longer line relative to the water depth, and it's greater than 1.7. I mean, very typically, the more shallow water mooring you have, it's going to be more likely you're going to have a larger scope. I mean, we've just got a bit of chain here on the bottom, and the acoustic release assembly and everything. I think we should just leave that the same. So let's save it. And the first thing we need to do, we need to run some wave states, but very first thing we need to do is run a static analysis. So we'll just export the static project. We don't need to change anything here. We're just doing a static analysis, and we'll let that run. All right, sometimes passed. Let's check and see what the static profile of the Wirewalker mooring in 50-meter water depth looks like. We'll open the results in ProteusDS. Just use default parameters for loading. Let's go to engineering view under display type, and then camera preset east, just so we get a nice side view of the mooring. And then this is the initial input. It's a pretty low tension mooring in this region, so it might look a little stepped, but it's just because it's very, very low tension through this region. There's the chain. The profiling line comes down to about here where the weight is. And then it gets stretched out a little bit with the relatively minimal current profile. So this is what it looks like under that relatively, mild current profile. And we're going to want to use this for the start of our dynamic runs. But first, let's just check the watch circle of that top buoy, and we'll do that with the report tool. So click on report, surface quasi-static cable single leg mooring, go generate, because we're just looking at a static result. So it's loaded up in our web browser here, and let's just check the horizontal excursion of the top component. That's the surface buoy. We're at 40, just a tiny bit over 40 meters, so that's pretty darn close to the expected result of 39 meters. So now we need to set up some dynamic runs, and we want to use the static profile that we've calculated as the start of the dynamic runs. And we're not sure which one will have the peak loads. I mean, we have some results, some expected results here, but let's set this up ourselves. So first we want to go back to our static project. So we go export final state. I'm just going to call this dynamic for now, and we're going to make some copies of this. First, we need to make a few changes. So we're going to close the static project. Again, just sort of, you don't need to really verify every time, but there's the starting point of that mooring. It looks just like what we saw in the static profile, thanks to the visualizer there. So as usual, we'll have to change, convert the static model to dynamic. Click on OK. We're going to run this for 500 seconds at 0.1 second interval as it's suggested here. And we're going to use a John swap C state. It's just an irregular C state spectrum. Resolve follower properties here. And the first set is an 8-meter significant wave height and 11-second wave. We've got 50 meters, 50 wave segments, so we're good to go there. But before I run this, I'm just going to save this because we want to make a few changes in terms of the wave seed. So I want this to be one unique wave realization for this C state, and then we'll check the other results as well. So I'm going to close this and make some copies of it. So you can do this pretty easily in Windows Explorer. So maybe to keep track of them, it's kind of handy to make a couple extra folders here. So we'll call this C state 8 meters. Call this dynamic seed 1. And of course, this just has our project files in it, nothing different. And I'm going to move that into here. And I'm going to manually make 2 copies of these folders. change this to seed 2. Change this to seed 3. Now, we can open each individual project and run it in Proteus Simulation Toolbox, but I'm going to show you how to use Proteus Queuing Manager for this one because it just helps manage things a little bit better. So you can go back into here. Now we've got seed 2, so it says use 222 for seed 2. I mean, these just have to be different numbers from each other. It's just as long as they're different from each other. That makes a different sea state realization. Now, if you don't have this open in Simulation Toolbox, you can just use Notepad or any other notepad editor and quickly change this. So we'll change this to 333. It's a little bit of a shortcut, only if you're comfortable doing that. I mean, the other thing to do is just open Proteus Simulation Toolbox, and you can change the number. You can see it's reading that file. Okay, so we've got these ones all set up. Perfect. Now, we do need to make some changes. I'm going to take one of these and copy it, Control C, and then let's make another set of sea states. Sea state 3 meters. Now, we'll open it up in here, and what's the other sea state that we need to run? It is 3 meter and 6 seconds. So let's change this to 3 meters, 6 seconds. Period. Perfect. I'll just make a couple of copies of those, Control C and Control V in Windows Explorer. Make sure these are different. And the only thing we're changing now is the wave seed, so I'm just going to save that here. And this is a shortcut. Again, you can just go into Proteus Simulation Toolbox. It's no big deal to do it that way. Now, we have 6 simulations to run, 3 in here under this 3 meter significant wave height sea state, and this 3 under this one, all set up and ready to go with a static profile. You can open all 6 of them and try to run them one at a time in Proteus Simulation Toolbox, or you can use Proteus Queuing Manager. And this is really handy because you can just highlight these 2, drag them and drop them in here, and then I've got a multi-core computer at my disposal here, so I can pick, a few of these and run them in parallel. And it's up to you how much you want to use. Obviously, the more cores you use, the more performance it's going to take up. So let's let this run for some time, and we'll come back and check on the results. Okay, some time has passed, and our simulations of this Wirewalker profiler mooring in 2 different sea states with 3 different realizations is complete. So let's take a look at some of the results. Now, in PQM, again, you can right-click and select View Results in Post-PDS. Let's just load the data and we'll get a quick look at some of the buoy motion and some of the results. So we got orthographic view on, let's change to engineering and then east. So that's the way the wave propagation and current are aligned, going from the left of the screen to the right. There's our downweight. And just very generally, we want to make sure the downweight's clear of the seabed, and things are looking pretty good, and generally the mooring is absorbing the motion from the surface wave, so that's good to see. Okay, and we can get a preview of what the tensions look like at the top of the mooring, and very generally it looks like there's some big action happening near the beginning, but these are all in newtons. These are pretty small loads, and it looks like they're capturing some pretty good characteristics. We're not missing lots of peaks, so that's good. These little peaks through here, nothing that looks too far off from the others, so that's good. So let's run some reports on this. Rather than loading each one and accessing the report tool through Proteus Simulation Toolbox, we'll do it in batch here. So do single leg mooring, and what I'm going to do is is we'll focus for now, just to save time. I'm just going to do the Sea State 8 results, but you could do both all at once if you wanted to. The loads are pretty low, so I won't turn on kilonewtons here, but like before, we're going to truncate the first 10 seconds. That's with wave ramping and getting rid of any transients at the start of the simulation. And we'll go generate. So when I dragged this one folder in here, you see 3 appear, and that's because the report tool is reading those folders and seeing that there's these 3 sets of results in there. So we'll click View on all of these, and they're going to load it up. They're all checked here, so they're all going to load them up in sequence here. So first thing is, let's check. Okay, so this is random wave number seed 333. So we're looking at the 8 meter significant wave height at 11-second results, so we should be seeing something like 1.4 kilonewtons maximum load at the top. So compared to the soft mooring, there's way fewer components, so you don't have to do as much scrolling, and that's what we're seeing there at the top. 1400 newtons, 1.4 kilonewtons. So it's good to see the expected result there. Now there's a note here also that says, hey, check out, there's some submergence that's happening. So this doesn't always happen, but it's good to keep an eye on this. The submergence probe is automatically added at the surface buoy for surface moorings. And you can see this maximum submergence, 1.5 meters, and you can kind of get an idea of that floater, minimum depth time, and time is around 25 seconds. So we've loaded the results. This is a good time to actually just take a peek and see if it's realistic here. So I'll switch to perspective view. I'm going to double click on the mooring here, and then let's jump to around 20 seconds. What's going on in the mooring around that time? So you can leave it on engineering view, or you can go to rendered view. I'm going to leave it on engineering view here, but I can tell you right now it looks like that's a pretty big wave coming at the mooring there. Yes, it's a very big wave. So it looks like just at the crest here, the buoy's submerging a little bit. So that's that could be realistic, and it's not a huge depth, but it's something, and you just probably want to make sure that. I'm not sure there's much you can do about the mooring design with that, because it's doing a pretty good job generally. It's just that one big wave that came by. So you factor that into the planning and use of the surface buoy that you have, because there's a chance that it could happen there. So yeah, other than that, let's check the other reports really quickly. So this is seed number 2 that we have, and we've got a maximum of 1.1 kilonewtons. That's expected. And then seed number 1 for the 8 meter 11-second result. We've got 1100 newtons. Oh, it's a smidge under that, 1.1 kilonewtons instead of 1.2 kilonewtons. That's pretty close though. All right, and then of course looking at safety factors for all these components, that's far above the breaking strength for many of these components. So that's very good. Really, I think what's driving this simulation is there's lots of good compliance in the mooring for absorbing the loads and the motion. So it's really just kind of checking buoy submergence, obviously keeping an eye on the loads, and then checking to make sure that the bottom weight clearance is good too. All right, thanks for watching.